All right, I see it.
Good to go?
Yep.
All right. Well, thanks to everyone that's joined. Appreciate you making the time to come listen to this today. My name is Nick Kaiser. I'm the Chief Technology Officer with Intergalactic. And in the presentation today, it's mostly focused, it's really a technical pitch at a high level, talking about constraining thermal problems in sky and space. I'll talk a little bit about our company, but to kick things off, just about myself. I've been with Intergalactic since it was formed about 7 years ago. And, prior to that, I had worked in aerospace thermal management, primarily with Amitech Aerospace and Defense, for about 10 years before that. So I've been in the industry about 15 years. My educational background is aerospace engineering, focused in thermal and fluids. So this is really what I've been doing for a while, and kind of excited to share our thoughts in this area and some of the cool stuff that's going on with this stuff. So I can get this to go. There we go. Let's get the right thing up here. So just a quick intro about the company, and I've got more at the end of the deck, detail-wise. But like I mentioned, I was working in large aerospace OEMs that have been around for a long time, doing thermal management work, and myself and colleagues there, recognized this growing problem. And this is a problem that's prevalent in really any industry, any engineering space. Thermal management is an issue, especially with the proliferation of electronics, consumer electronics. Now there's this huge growth in electric vehicles and all sorts of high power systems. Anywhere there's this kind of growth going on, there's thermal problems. And it's becoming it's a constraint everywhere, but in aerospace particularly, it's a constraint, for two reasons, really. One, there's the problem itself, which is getting worse and worse. On an aircraft, you're very limited. I'm sure as many of you know on the call here, you're limited on size, weight, and power all the time. And increasing thermal loads demand bigger and bigger systems, and that's really the root of the constraining problem. The other part of it, though, and what led to the formation of our company, is there really hasn't been a whole lot of innovation in the space. I mean, you're seeing some stuff now, really over the past 5 to 10 years, some development, a lot of it we're working on. But before that, really the solution has been take literally 1950s technology and just continue to brute force scale it. And that's really not a viable solution. As you get these higher loads, there's just not room or power or weight budgets on these aircraft or spacecraft to tolerate that. So new technology is needed, and that's really what led to the formation of the company. And yeah, I kind of skipped ahead here. So we'll get right into it. Mostly what I'm going to talk about today are some specific examples within aerospace. So I mentioned, this is a problem everywhere, all sorts of industries, all throughout aerospace in particular, which is really what our company is focused on. But three particular applications, and we're working in all of these where it's an especial problem. Electric aircraft, whether you're involved in it or just following the news, you probably see a lot going on with eVTOLs. Those are like these electric air taxis, like the picture there in the bottom right, or taking conventional fossil fuel aircraft and converting them to hybrid electric or fully electric. And even before that, something that's been going on really the past 20, 30 years are more electric aircraft. So a lot of the newer platforms flying around today, like Boeing 787, for example, a lot of legacy hydraulic systems and things like that have been replaced with electric systems. And all those electric systems demand a lot of cooling, and it's really a problem with fully electric aircraft. It's a constraining problem, particularly around batteries and managing all the electric loads on the system, or also fuel cells, which I'll talk about in a little bit. Another one on the left-hand side, this is another thing you might see in the news, something that the military has been working on for some time, is making futuristic laser beam weapons, basically. Taking high energy lasers and using them to either disable things or even the higher power lasers blow things up. There's been a lot of work with these on ships. The benefit of being on a ship is that you have a huge power supply, either in a nuclear reactor or a large engine, and you have the ocean for cooling. When you put it into an airplane, you don't have either of those things. So there's really two big constraining problems there. One is power generation, which is kind of its own separate thing, although it can be integrated with thermal management in some cases. And then there's the cooling, and it's really a major constraint to making that viable. And there's a lot of interest in making that viable because it brings a lot of capability to the military. So there's a lot of interest in that space as well. And then last but not least, going out into space. Space is full of its own thermal problems, but one that's of particular interest lately, and this is another thing you might see in the news with the Artemis program, there's a big push to get back to the moon. And it's not just for the sake of exploration. There's a lot of interest in actually putting permanent moon bases on the moon, both for scientific exploration, but also industry. There's a lot of interest in mining and other activities up on the moon, and also as a launch pad to future space exploration. And the moon is a very inhospitable place for a number of reasons, and one of the big ones is the thermal environment. So we'll talk about that some more as well. So I think we have a pretty, I'm not sure the makeup of the audience on the call today. It's probably a pretty broad range of people. So I wanted to start out at a really high level, just talking about what thermal management is. And bananas probably don't make much sense, but one of our customers that we work with, they described thermally caring for a electric aircraft battery is a lot like trying to take care of bananas. They're very temperature sensitive and temperamental, and holding them at the right temperature and caring for them will help preserve the bananas and make sure they get to their destination. It's actually very true for a lot of the things that we really do cool in aerospace, whether it's precision electronics or occupants. We've got some item that we want to hold at some specific temperature, and that's what the T is there. And then to do that, we really have to either take away heat energy or add it back in, depending on the case. A lot of times we're talking about cooling because we're pulling heat away from something that's generating a lot of heat. Take a directed energy laser diode, for example, which I'll talk about more in a minute. A lot of time we are taking away heat, but on the moon in a lunar night, it's extremely cold, and we're either trying to hold on to heat or even bring it back in. But when you take thermal management, this is really what it boils down to: trying to hold some temperature for some mission reason, and then accomplishing that by either taking away heat or adding it back in. So drilling in a little bit further, and this will start leading into some of the solutions as to how you tackle this, but breaking down the thermal management problem a little bit more, there's really just a few constituent parts to it, and each can be attacked with specific technology for those parts, plus the system integration that pulls it all together. So the first thing is, and I'll talk about this just in the context of cooling, if you're heating it, it's just backwards. But we have something, bananas, microchip, an occupant, laser weapon, whatever, something that's generating heat. And the first thing we have to do is remove the heat from that source. This is actually one of the most challenging problems out there today, particularly with high power electronics. So like you look at your smartphone or a laptop, there's a really, really small component on a board, and getting heat out of that component is a real challenge because for a number of reasons. It's very, very small, but a lot of microcontrollers and circuit boards and things like that are really not conducive for cooling. They're made out of plastic or some other insulator, and getting heat out of those devices is a real challenge. And that's the case for really a lot of the applications that I'm talking about today. A lot of the legacy solutions are cold plates, so like a hunk of metal that a chip is mounted to, or like a fan blowing on it. Things like that are kind of the legacy solutions, which steps kind of into the next part of the challenge. So once you pull heat out of something, you have to carry it away. If you don't carry it away, then the whole region will heat up. Like if you have a big block of aluminum and you mount a chip to it that's generating a lot of heat, it'll help for a while. The aluminum will soak up heat, it'll pull it away. There'll be some natural convection off the aluminum, assuming it's out in the open air. But eventually that whole thing will heat up. You have to pull that heat away and keep doing it at the same rate that heat's generated to hold equilibrium. So that's the next, link in the chain, if you will. And, traditionally this is like air, and that can be combined with the heat removal in the step one. Like I mentioned, like a fan blowing on a component, that's using air to convect heat off the component and carry it away somewhere. In liquid systems, you might have a coolant like ethylene glycol water, or an oil like PAO or engine oil or transmission oil that's running through some cold plate and carrying it away somewhere else. And those are still very useful tools. And a lot of solutions we work on still utilize elements of those. But like I mentioned in the beginning, taking that same technology and just scaling it up and up and up for these, exponentially increasing heat loads gets to a point where it's just not viable anymore. You end up with just, huge fans or huge pumps and lots of liquid and coolant, and it's getting, becomes a problem in and of itself. The next link in the chain, and this is not always required, but it's a concept called temperature lift. And this happens when you need to hold something at a temperature colder than whatever your heat sink is. I'll get to that in a minute. At the end of the chain, ultimately the heat has to be rejected and dumped somewhere. A lot of times that's ambient air. It could be water in the ocean, the ground, fuel in an aircraft. There's all sorts of places where it goes, but ultimately it has to go somewhere. And depending on the temperature of that sink, you often need to cool your target device below that sink. And that's when you need lift. So that's most commonly seen in a refrigeration system. So air conditioner in your house or your car, a refrigerator, vapor compression cycle, refrigeration systems are all over the place. And that's usually the main approach. There are other systems used on aircraft, a lot of like commercial aircraft and stuff like that. There's air cycle machines that take bleed air and use thermodynamic properties there from the, knocking down the pressure and stuff like that to provide cold air. There's thermal electrics. There's other stuff as well, but vapor cycle is probably by far the most prevalent for that step in the chain. And that's a very heavy, high power draw part of these systems. It's usually by far the most. So there's a lot of room to optimize and improve on the existing technology and look for new options. And then the last link in the chain, like I just mentioned, is ultimately rejecting the heat somewhere. So you've taken it away, you've transported it, you've if it's running through a vapor cycle system, you're adding even more heat to it because you have all the waste energy from the whole cycle there. And you've got to take all of that and reject it somewhere. And in an aircraft flying around, most of the time you're rejecting it to air. Whether it's driven by a fan or it's ram air, you've got a scoop on the side of the plane and it's just taking air from the velocity of the aircraft. On some military aircraft and others, sometimes the fuel is used, although that, has its limits. There's only so much fuel on the plane. If you have a geothermal heat pump, you can dump it into the ground, but that's obviously pretty limited, for really only for ground applications. And then in space, it's especially challenging. There's no atmosphere. So almost always you're radiating it out into space. You just got a panel and you're pointing it out into the cold, dark void of space and radiating all that heat out there. But these are really the four, major chunks in the chain. And, when we get to the solution part, we'll talk about, what's being done for each part of this. But before that, just getting into the three problems that we're talking about today, more specifically, first with directed energy constraints. So, really at its heart, it's a fairly simple technology. You've got a laser diode that's generating very high intensity focused light, and it's an electronic device. They're not particularly efficient. I mean, it depends who you ask, but oftentimes are less than 50% efficient, meaning if it's 50% efficient for every watt of light, there's going to be a watt of waste heat. And that heat has to be carried away from the diode and has to be held at a certain temperature for it to work correctly. And the lasers that, to make it a weapon grade laser, you want a really, really high powered laser. And the loads really get wild. So, we've been involved in some early work around this with some demonstrators and stuff like that, where they're working on 25 kilowatt lasers, and that's, really pretty limited in its capability. But even that generates 25 kilowatts of waste heat that has to be carried away, which is a lot. The goal is to get up to much higher power levels, hundreds of kilowatts in the not too distant future. And then on the right hand side here, I've got a little snippet from a recent AFRL paper. There's goals over the next 30, 40 years to get up to a gigawatt laser, so 2 orders of magnitude higher, which is a ton of power. And then the other thing, there's 3 bullets there. The bottom one is another big thing, and that's, we want to make them really, really high power and tiny. So to do that, you need really, really efficient thermal management to be able to pull away that waste heat and in a small package and make this work. And, aircraft of today don't have thermal management systems that can come even close to handling these kind of loads. And there's problems all over the place. It's hard to get heat away from the diode, and then getting it off the aircraft is a challenge as well. So really a lot of constraints to work through here. Like I said before, like ultimately you have to reject it somewhere. In the case of this, you're usually rejecting it to ram air around the aircraft, which might even be supersonic, so it's heated. But this is a huge constraining problem. And in some of our conversations with AFRL, the Air Force Research Lab, and other groups, like there's really 2 main constraints to making this work. One is power generation, and the other is thermal management. So this really has to get solved for this to be viable. The next is electric flight. There's just so much activity in this space right now, a lot of excitement and energy, all sorts of new companies popping up with these air taxis, and converting traditional jets over to electric or hybrid. Lots and lots of work, which is all pretty exciting. And all those electric systems need cooling. Motors, power systems, all electronics, all the accessory systems, and then especially the batteries, which I'll talk more about in a second. So all these things need cooling. The real challenge with making electric flight work is weight and space. We've all been spoiled for a long time with fossil fuels. They're very, very energy dense. The amount of power you can get out of a per unit mass is very high. And the other thing on a plane, you put a ton of fuel on it and it burns it off over the course of the flight, so the plane gets lighter. That's not the case with batteries. So, there's still quite a long way to go. I mean, it's close and workable for some of these air taxis, but for long range aircraft, it's still a lot of work to do there. But it's just especially critical to make the batteries and everything as small and lightweight, and all these auxiliary systems, including cooling, which is a big one, as small and efficient as possible, because any weight you add and any parasitic power draw is just limiting range and capability of the aircraft. And then specific to batteries, thermal management is a real enabler for batteries. So, lithium-ion batteries, which are really ubiquitous right now for use on all these electric mobility platforms, cars, and all these aircraft applications, they really like to be held at a specific temperature. Like I was talking about the bananas before. The current batteries that are used all over the place really, like to be at 25 C. The next generation, which is solid state batteries, they like to be held hotter at 100 C. In both cases, they generate a lot of heat though, so heat has to be pulled away, and they have to be managed at those temperatures to work well. And if you do it right, it helps in a lot of different dimensions. So for one thing, it improves energy density, which is huge. So I was at one talk last year where I heard on a panel that if you have good thermal management of a battery system, in some cases you can cut down the amount of battery you need by up to 50%, which is huge because these batteries are very heavy. Another important consideration is that you need to have isothermal conditions across all the cells in the battery. So these things, you have this big battery pack. It's made up of thousands of little cells. They look like, C or D batteries, and many, thousands of them. They all need to be held within 2 to 3 degrees C of each other, so that you have even discharge and prevent potential thermal runaway, which is a safety issue. And the last thing is there's a significant 50% or more improvement in battery life if you have good thermal management on batteries, which is another big concern. You hear about that all the time. there's a lot of rightful concern about how long these batteries last, and then can they be recycled, can they be disposed. So thermal management is a real enabler to help electric flight work. And then there's the lunar surface, which is really often its own, it's literally off-worldly. The moon is a very inhospitable place. It has a unique, day cycle. The lunar day is 15 Earth days long, and the lunar night is 15 Earth days long. During the day, it's very hot. Much like Earth, it depends where you are on the moon. The equatorial regions can be all the way up to 250 F during the day, and in the polar regions at night, and even in the equatorial regions, it gets very cold at night, but it can be as low as negative 330 F, 70 Kelvin. So huge swings. During the day, everything's getting roasted with radiation from the sun, and at night, it's just bitterly, bitterly cold for a long time. And there's a lot of other challenges as well. Like I mentioned before, there's no atmosphere on the moon, so you've got to reject the heat elsewhere. You don't have that. Moon dust is a real problem. It collects on radiators, it gets in things, it's abrasive, it causes a lot of environmental issues with equipment that you put up there. There's radiation, beyond thermal radiation, there's radiation, which is damaging to electronic equipment and for people, and that's a real consideration to put into any equipment that goes up there. Obviously, very difficult or sometimes impossible to maintain or repair equipment, and reliability is absolutely crucial. Especially when we have people up there, things really just cannot fail, or humans' lives will be put at risk. And this goes for any aerospace application, and you saw it in the previous two, but for space, weight is even more important. You have to launch this stuff off the Earth and get it to the moon. It takes a tremendous amount of fuel and power, and it really limits how much payload is available. So weight is at an absolute premium, and any kind of system in here needs to be as efficient as possible. So that's kind of an overview of the problems. Now I'll start talking about the solutions. So in all three of those applications, and really a wide variety of aerospace applications, like I mentioned, the problem breaks down into a lot of similar chunks. And the overall general solution also can break down addressing each of those chunks, as well as system optimization and some overarching themes. And I'll talk about all of these. So, first, getting heat away from the source, making that as effective and lightweight as possible. Then there's another element which was not in the in the problem part, but it's part of a solution for a lot of this, and that is being able to store heat. A lot of loads are transient, so they'll have big peaks, particularly like the laser weapon example. You have a high energy laser and it discharges for 15 seconds and it's off for a while. It's got some duty cycle. So you have very, very high intensity load and then nothing. If you're able to use heat storage, you can kind of flatten out the load profile and reduce the average system demand instead of sizing a thermal management system to operate at that peak load all the time. The next thing is the transport. Making a system that's as efficient and lightweight as possible to carry the heat away from source to sink. And then same thing goes for temperature lift. Vapor, like I mentioned, that part of the system, if it's required, is often the heaviest and most power intensive, sometimes by orders of magnitude. So there's real importance to focusing on reducing that as much as possible. There's also, and I don't really get into this too much in this presentation today, but there's an opportunity, particularly with the really high load stuff, to recover some of that heat and use it again, whether it's for heating somewhere, if you have a cabin, for example, and this is actually how some of the newer electric vehicles are working. They'll use a heat pump to recover waste heat from the battery and the motors and use that for heat in the cabin. There's a real opportunity for that as well in aerospace, or even generating electric power. It's challenging because the they call it quality. The quality of the heat available is not very good. It's relatively low temperature, but there are some options there to be able to recover that, and that's something that we've started to look into a little bit. And then lastly, is rejecting heat as efficiently as possible to whatever sink you have, whether that's air, water, void of space, doing it as efficiently as possible. And then tying all these things together, there's a few overarching themes. One is really leaning into software optimization. That's a tool we have available today that wasn't available that long ago. Optimizing each of these elements and then also pulling the whole system together. In the past, a lot of requirements are developed at the top level and then flowed down to the components, and they're all developed in a vacuum. But there really is a lot of opportunity with the systems engineering side and optimization to help improve, everything we're talking about. The next is materials. We have composites. There's all sorts of stuff coming out that's much lighter weight than metals. There's work to be done, particularly with regulatory bodies and things like that in aerospace, but there's just so much opportunity to pull out weight just by changing materials. So things that are available today. So that's another area of focus. Another one, and it's kind of funny because software is certainly not a new thing, embedded control, but this is getting into problems that are more specific to aerospace. It's an industry that's slow to adopt things. Just by applying intelligent controls, we're able to really reduce power consumption in a lot of systems. A lot of legacy ECS solutions, for example, will run fans and compressors and pumps at the same speed all the time. So the power draw is high all the time, when in reality, max load is pretty infrequent. So if you're able to just use basic software controls, you can really reduce the amount of power draw, on average. And then lastly is just a full embrace of electric systems, particularly high voltage DC systems. Everything's heading in that direction, especially electric flight stuff, high voltage buses, everything's electric, and just leaning into that really helps a lot of stuff advancing. So getting a little bit more specific to each of these applications, on the directed energy front, and I'm just going to again walk through the same kind of chain of things. The first thing is getting the heat out of the diode. A lot of that's done today with a cold plate, metallic cold plate. Looking at more efficient materials, whether it's different metals or even composites, which I'll talk about a little bit, that can help just pull weight out of the element and make it more effective. Or even better, having direct flow through in the element. So we have supported some programs where there's optical items that are directly cooled by a fluid. That's really the best thing to do there. The next, and this, the phase change material thermal battery is key for this, because like I mentioned, there's a very high intensity load that's relatively short duration. And, to size a thermal management system that holds that peak load all the time would be massive. Using a phase change material thermal battery to absorb that load and then let the rest of the system run at some lower steady state all the time really helps size down the whole thing. So that's key. And you kind of see that little diagram on the bottom there. Those red bars are the pulses, and you can see the average load is the blue. So you kind of level the whole thing out, and you can really downsize the system by quite a bit. Now, getting into the heat transport, something that really can help a lot, and something that we're putting a lot of time into as a company, is traditionally the heat transport is really air or a single phase coolant. Switching that over to a pump two-phase solution really can reduce the size and weight and power draw of the system by a lot. We're really talking like orders of magnitude, and that's key here because we're carrying hundreds of kilowatts, potentially up into the megawatt range in the not too distant future. And doing that with a traditional liquid system, you're talking hundreds of gallons per minute, high pressure drops, lots of power, and you can literally divide that by 10 if you can convert that over to a pump two phase. So that's a huge potential option there. And then if lift is required, which is not particularly common with these because the loads are so high, and if you're flying at higher altitudes, you have colder air available. But there are applications popping up where that is desired, whether it's because you're flying at lower altitudes or supersonic flight. You really need a very, very high efficiency vapor cycle system. And a lot of that is, we're starting to get into really high speed, lightweight, efficient centrifugal compressors that are really compact and small and efficient for the amount of performance they're providing. And that's kind of the key to that. And again, like I mentioned earlier, there is an opportunity to recover heat there, which would be huge, but there's more work needed to mature that technology. And then lastly, almost always this heat is being rejected to ambient air around the aircraft, which requires some kind of fluid to air heat exchanger. Another core element of our technology is what's called a microtube heat exchanger. These are much smaller and lighter, 1/2 to 1/3 the size and weight of brazed plate fin heat exchangers, which are kind of the gold standard throughout aerospace for a long time. And that's another enabler, being able to efficiently reject that heat to air without having a prohibitively large and draggy heat exchanger on the outside of the aircraft, really is key to making this work. For electric flight, a lot of the systems on board that are generating power, again, it's going to be a lot of cold plates. There's a ton of opportunity to go over to composite cold plates here, with the loads being not as high as directed energy, for example. And then on the battery side, today a lot of it's cold plates, but there's a huge opportunity to convert to flow through, and particularly if it's using a pump two-phase system, like I mentioned before. And that brings a few benefits to the table. Again, much smaller, much lighter, lower flows, less power. That's huge for this. But in the case of a battery, you need to hold all those cells at the same temperature, like I mentioned before. And if you're using two-phase refrigerant boiling off through a battery, that's going to stay at the same temperature all the way through. And so you're kind of, getting two big benefits there out of one. And also refrigerants are dielectric, which is a benefit in batteries as well. And things are kind of heading in that direction. So if you look on the bottom left, there's a little chart out of a recent report from IDTechX. You can see that refrigerants, recently, especially in China, where there's a lot of EV development, are starting to take off as the primary thermal management for batteries. So a lot of interest in that area. And then phase change materials are helpful here as well, for flattening out loads in an eVTOL, for example. There's peak loads during takeoff and then also during charging. Charging's it's not as helpful there, but during takeoff for sure, you can help flatten out the load profile a little bit and maintain an isothermal condition throughout the battery. And then same thing if there's lift required, high efficiency vapor cycle system. And similarly for rejecting heat to ambient, you're relying on efficient and lightweight microtube heat exchangers. And then on the moon, there's a really removing heat from the source is a common theme. Cold plates again are ubiquitous. So you're looking at either lightweighting that through a composite cold plate or some other solution with materials, or looking at a flow through. And each of those provide weight and size and performance benefits. In the lunar environment, where you have the huge thermal swings, phase change material batteries can be really helpful. You can collect heat during the long lunar day, store that, and then save it for the nighttime when you need to keep things warm. There's also some interest in kind of a geothermal approach where you store heat in the lunar soil and then bring that back up to the surface at night when you need it. But it's all about taking that heat from the hot day and then storing and holding onto it when you need it to get through the cold night. And then as far as heat transport, again, pump two phase, it brings the same benefits as the other two applications. On the moon, though, it brings another benefit, and that is, a lot of coolants that are used on Earth, they don't do very well when it gets really cold. They freeze, and oils become really, really thick. Refrigerants are really able to go down to very, very low temperatures without freezing. So that's a real benefit for getting through the extreme cold conditions. And then lastly, aside from potentially using the soil as a thermal sink in space, really the rejection option is radiating out into space. And, we're looking at applying microtube technology into a radiator. Traditionally, those are just big blocks of aluminum that are flat, but there's a lot of room to, increase surface area and lightweight those devices using microtubes and/or composites. So then I'll talk a little bit about each of these elements that go into this. So I talked about systems engineering and optimization. That's huge. So, using model-based design, creating, so-called digital twins of the system is really helpful in optimizing the whole system and all the constituent components. You can do this with existing technology and yield some really big benefits. I mean, it's hard to put numbers on it sometimes because it depends on the system, but it's not free. You have to put the work into this, but it is almost free in the sense that you don't have to invent anything new. So this is something we do on really every system and product that we're developing. The next is materials. So again, metal replacement wherever we can, embracing composites. And you think in composites, you don't think of having good thermal properties, but that's actually starting to change. There's a lot of work being done and some new materials available within composites where you can get pretty good thermal properties that are coming up, not quite to parity with aluminum, for example, but getting close. And given the weight benefits, there's some really interesting opportunities to use composites, not just for structures, but also for some of the thermal elements. And I mentioned that, having to do with cold plates and also potentially for radiators in space. Again, really leaning into electric. We've been on board with this since our company was formed. The writing is just on the wall. Everything we develop is, embracing software and embracing high voltage DC power. So, pretty much all the newer military applications we work on are 270 volt DC. And then this electric flight stuff is even higher, 500 to 800 volt DC plus. And that in and of itself brings weight benefits running up in these higher voltages. And then, building on software, some of these applications, we need to hold electronics at very precise temperatures, whether that's a laser diode or some piece of avionics or an optical sensor. There's times where we need to use feedback loops and software to be able to hold something at a very precise temperature. So there's some cases where, we're able to hold temperatures to plus or minus 0.1 C if we need to, just through feedback loops and software. So that's another element that's there if needed. And then also just running the system only as hard as it needs to run. Again, that's a fairly simple thing, but it can really save a lot of power instead of just having a old school, quote unquote, dumb system that runs at full power all the time. And then I mentioned microtube heat exchangers a couple times. So this is really the core technology that got our company started. Aerospace has been using plate fin aluminum heat exchangers, almost universally for a long time. And they've been very good. They're very high performance as far as heat exchangers are concerned, but they have their own limitations. And we've brought to bear this style of heat exchanger and matured it and are starting to deploy it out into aerospace applications. And we're able to see very, very significant decreases in size and weight, 50 to 50% more. And that's especially important when you're talking about some of these things like rejecting heat to ram air, because huge loads being rejected to ram air on an aircraft, and hanging a gigantic heat exchanger off the aircraft just creates huge amounts of drag, knocking down range and performance and things like this. And this really helps enable that. We talked about phase change quite a bit. This is not a new concept. And, there's other groups that are working on this. It's, a lot of interest out there in phase change materials and thermal batteries and stuff like that. But we specifically have taken our microtube technology and deployed it out into phase change thermal batteries. And the benefit there is a lot of these phase change materials, they're great at storing energy, but they're terrible conductors. So it's very hard to get heat in and out of the material. And that's where there's a lot of room for improvement. both for the performance of these, but also for making them lighter. You know, there's a certain amount of material you have to carry for the thermal properties you want, but the heat exchanger and all the stuff around it can really be optimized. So that's something that we're working on as well. That's a little video of it melting, if you can see it. And I talked quite a bit about pump 2 phase. This is really exciting technology. Again, you know, it's something that's been talked about for a while. There's some work being done here and there, but getting this and really deploying it out in aerospace is going to really be an enabler. Again, you know, we're talking order of magnitude reduction in size and power draw. So take a liquid pump glycol system, and for the same thermal performance, you can divide the flow rate by 10. So that's bringing, you know, huge advantages, something that we're really interested in. And this is some exciting technology that's going to be really applicable to not just the applications talked about today, but you know, even more broadly than that. And then, like I mentioned before, using composites as actual thermal materials, which is really exciting. You know, composites really, you know, obviously the big benefit there is much lighter than metal. And, you know, that's been great for structures, and, you know, it's being adopted more and more and more, but, you know, again, traditionally the thermal properties are not good, but that's starting to change. So there's a real opportunity, and this is something else that we're working on, to actually make partially or completely composite cold plates, and potentially radiators in space as well, and leveraging specific properties and different, you know, axes and things like that. But very interesting, exciting material advancements around this space. And a few other composite things as well, you know, obviously like structures, as mentioned before, but enclosures for batteries. You know, there's all sorts of stuff where, you know, composites replacing metal really saves weight and helps enable all the applications that I've talked about today. So that was pretty rapid fire, and we're going to have time for questions here in a second, but just a little bit more about us before we go there. Like I mentioned, the company is about 7 years old, which is a blip in the aerospace timeline, but you know, we've really accomplished quite a bit in that time. We're based in southern Utah. We have a sister company called RAM Manufacturing that you might be familiar with. That's a 40+ year aerospace solenoid valve company, and we're co-located in their building with our production space. We're AS9100 certified. We have been for about 3 or 4 years now, and we're really working with a pretty wide variety of primes. You know, we got our beachhead with defense aviation, you know, with a lot of the U.S. defense primes, and we've kind of expanded out since then. So we've got a lot of really exciting work going on. I think, you know, all the companies on the page here are either actively working, you know, with on a contract or are engaged in talks close to a contract. So we've built up a pretty broad base of partners. And then on the bottom right, just some examples of things that we have fielded. You know, so in the aerospace timeline over 6-7 years, that's only enough time to get through development and qual, and now just start getting stuff out in the field. But, you know, we have done some work on direct energy stuff, which was discussed today, military rotorcraft, and also some pod thermal management systems. So that's kind of our, I won't say legacy, we've only been around 7 years, but kind of our legacy equipment. And then a lot of the stuff discussed today is the newer stuff that we're working on for the next generation. So that is the presentation, and would be really happy to take on any kind of questions there are.
Want to start there?
All right, let's see. So the first question is from Mohammed. What type of material is preferable for using in 3U CubeSat satellites, and what material should we use if we want to test the satellite with electronics and a thermal chamber with a temperature range from -40 to +60 C? That's a great question, Mohammed. I think it'd be great if we could connect and get on a call with myself and some of my space colleagues because I think depending on what you're trying to do, there could be some, drastically different materials, depending on what's going on, whether we're trying to conduct heat away or insulate or all of the above. But would love to connect and talk some more about that. And then Mohammed Rezvani asks, what type of PCM is suitable? How to balance between weight and efficiency of PCM? So the most common PCM and what we're really working with primarily now are like paraffin waxes, and that's really out of convenience. They have a high, latent heat for, when in melting, and you're able to tailor them for specific melting points. So it's very easy to work with. There are some other things that we're looking into. There's some thermochemical stuff that's coming out that's newer, even water in some applications, but that's primarily what we're looking into now. And as far as balancing between weight and efficiency of PCM, that's really an optimization analysis depending on what the load profile looks like or the duty cycle of the system. And that's something that we can look into with you if you're interested. We can look at your duty cycle and then figure out, because it's not. There are cases where it's not appropriate, right? Like if you have a very flat, duty cycle, it's not appropriate. But depending on how transient it is, we can run some analysis and look at that. And that's for eVTOL specifically, yeah. Rahul would like to connect. We have a compatible solution that'd be of interest. Yeah, that'd be great. Let's do it. Please reach out. But by the way, I've got my contact info on here. Feel free to shoot me an email or give me a call or connect through Asher. Happy to talk with you. Aloha, John. I don't see funding opportunity RFP on the website. I have an advisor who is JPL rocket scientist, equated with Miss Brittany Zimmerman at Yumet, now living in Poa, Hawaii, who boasts here contribution to NASA. FYI, Bigelow Aerospace has telemetry station here on Big Island. You interested in engaging setting up a satellite office here? Yeah, I'd love to. Yeah, let's talk. I'd love to learn more about what you're interested in, John. That'd be great. Tyler Christensen, impressive presentation. Do you foresee a lot of growth in employee count and associated support services as you continue to grow? Yeah, absolutely. We have about 60 people in our company today. We've grown quite a bit, over the past few years, especially as some of our stuff approaches production, and we're seeing a lot of interest. So, yeah, for sure. I mean, that's our goal, is to keep growing. So if things keep going well, that's to be expected. We have two methods of, Dan Cohen says, we have two methods of protecting surface materials while improving thermal efficiency without any weight. Yeah, that would be great. Would love to talk to you, Dan. Again, got my contact info here. Please feel free to reach out directly to me, email or call, or you can connect through Asher. Mohammed, let's see. Thank you. We'll connect. I'll write you an email. Yep, sounds great. How Hareshikash, I apologize if that's way off, but how affordable are these temp stabilizing technologies? So, honestly, the software element, there's so many considerations there, right? Depending on the application and what, because we work in a wide variety of stuff where there's a lot of, certification or data requirements and things like that. But the technology itself, we've developed it and it's not particularly expensive. And, we can certainly provide more information based on your application. So please reach out to us. David, what sort of Z conductivity are you seeing for organic matrix composites that enable consideration of space radiators? I also see that are modified with Z fibers or resin additives. Yeah, David, I would love if you reached out to me. I don't have that off the top of my head, but we can connect with, again, with my space colleagues that have been working on this more closely and get you some of the specs there. And lastly, Micah Peabody, is AM a point of interest? Yeah, absolutely. We've done some additive work, particularly with like structures and ducting, some of this carbon fiber stuff with fan blades, some metal additive for some heat exchangers and things like that. But yeah, it kind of goes back to the materials theme. We see a huge future in additive for all sorts of stuff. I mean, obviously heat exchangers, but really a lot of different elements to go into the system. So super interested in that. And if you want to connect, please reach out. Would love to talk.
Okay. I think we can skip this one potentially. I just want to read that one out loud.
Mahalo, John. Mohammed, yeah, my email address is out here on the screen. It's Nick K, Nickk at ig.space. All right.
Perfect. Well, thank you so much for this fantastic presentation, Nick. And I'm sure you're gonna have quite a few people already in your inbox. And yeah, really appreciate it. That was extraordinarily informative. And stay tuned for potentially a future webinar with Intergalactic. Hopefully coming up soon. So have a good one, everyone. And thank you again, Nick. Unless you have any other last words.
No, you bet. Thanks everyone for coming. Thanks, Asher, and look forward to hearing from anyone that reaches out.
Yep. Have a good one.
Take care.
Bye.